So in its basic form, what is kinetic energy?
Okay, you just asked.
Yes.
Energy of motion.
I like to see the hands. That's good. Yes, energy of motion. So when we're talking about the energy tied up in something moving, whether it's a shoe kicking someone, or even like a proton zipping across through the air that we can't see, that has kinetic energy, and it's described the same way. And we saw that yesterday, that it's related. Work is related to kinetic energy by that formula of 1/2 mv squared. That describes how much kinetic energy something has. Or if you do work on it, that's a way to describe how much energy you've put into it based on how much the kinetic energy changes. This is a very good question, not one that many people got correct. Using the work energy theorem, which says that work is the change in potential energy plus the change in kinetic energy. And we're really only looking at the kinetic energy for this part. So if we're looking at work as a change in kinetic energy, that'd be the 1/2 mv2 squared minus 1/2 mv1 squared. Just looking at what did it start with, what is it now? Which does more work? Accelerating an object slowly from velocity 1 to velocity 2, or accelerating it quickly between the same two speeds? Noah, you had a really good answer on this one, I thought, if I'm remembering correctly. How did you answer that one?
Acceleration is not a factor in calculating work.
No acceleration, right? This is one of those path-independent things. Doesn't matter how long I take to go from V1 to V2, the work is the same because no acceleration in here. We're going to use that, and the same thing goes for if I'm lifting something, say from the floor up to 2 meters. I know that I've got a work that's mgh2 minus mgh1, taking the potential energy that it started with and the difference from what it has now. So I'm just looking at my work as how much did that change. Doesn't matter the path I take either. I could do it really slowly. I could go like this. It's how much energy am I adding, not how long does it take me. That's a different question that's called power that we'll get to later. But neither one of those has anything to do with how long it takes or even what path it takes during that. 8 and 9 were fine. Gravitational, so this is another really good question that is not an obvious one. Is the gravitational potential energy of an object, a ball held above a table, for example, an absolute amount? So what that means is if it's always in this location, right here, say, will it always be considered to have the same potential energy? You're shaking your head no, Morgan, why?
Well, because you get other factors like if you have a fan blowing up that causes extra wind resistance, or
this is our factor or work, but factor for potential energy. Where does the wind resistance fit into that?
I changed my answer to gravity could be different on a different planet.
Okay, but that would probably put it above a different table too. So you're right. So gravity could change. Wait, no.
The surface is going to fall through change up or down.
I could leave my ball here and move my table. Then would it have the same potential energy? No. So potential energy is actually not an absolute. It always depends on what are you measuring from and what are you measuring to, the difference between the 2 points, rather than an absolute value that it's always going to be this amount. So if I'm comparing it to the tabletop, it'd be one thing. If I were comparing it in the same location to the floor, or if there were a basement floor below us to that, could be very, very different. So not an absolute, depends on what you're measuring from and what you're measuring to. Both that and the acceleration question here are both subtle, but both important to understanding it. Total mechanical energy, you were good. That was the total potential and kinetic energy. Under what conditions is the total mechanical energy? So all of the kinetic energy and all of the potential energy conserved. Or when would it not be conserved? Alex?
It would be conserved when when there's no non-conservative forces acting on it.
Right. And so what was the non-conservative force? What does that mean?
Like friction or a force that would change the amount of work.
Right. It's something that would take energy out or put energy into an object. So like friction would be is a good example. We're very happy to see you. We were talking about you just a little while ago.
Well, you don't need to film me.
I was reasonably confident he wouldn't watch it. So, and then the next question: what does it mean that this energy, that this mechanical energy, is conserved? And a lot of you said it stays the same. What does that mean? What that means is that the total amount of kinetic plus potential energy, which we were calling mechanical energy, this mechanical energy doesn't change. These could individually change. If kinetic energy goes up by 50 joules, well, then potential energy must have gone down by 50 joules, but their total stays the same. That's what it means when we're talking about conservative forces, that it all stays in here, but it can still shift back and forth. And a good example of that is this ball. I'm going to do a non-conservative force. I'm going to add energy to it when I throw it. But after I release it, as it's going up through the air and as it's coming back down, it's conserving energy. A little bit of drag that we usually ignore. But it's conserving, so it's taking its kinetic energy, changing it into a like amount of potential, and then back into kinetic. That was like the bounce homework that we did. And then you've got the non-conservative force, me adding energy and then me taking energy out of it when I catch it. But as long as those non-conservative forces aren't present, it's the same. Kinetic and the total kinetic plus potential energy remains the same. And then we had two last ones. And again, some of these got answered very well and some not so well. The law of conservation of energy states that energy cannot be created or destroyed. Explain how these situations don't break that rule. That is a universal rule. It can't be broken. So really we're looking for, how doesn't this break it? And so the first one is that the sun creates a lot of energy. It's giving off energy all the time. A lot of energy all the time. 3.8 times 10 to the 26 joules every second. A lot of energy. And it's seemingly creating it from nothing. Did you have?
I had a question there.
Oh, yes. What was your question? We'll get to it. Back.
Does that mean that you reach terminal velocity when potential energy is zero?
No, potential energy still might be very high, but you've got a non-conservative force, drag, also acting on it. So it's taking energy out of the system at basically the same rate that it's transferring from potential to kinetic.
And the sun makes energy via fission?
Sun makes energy via fission, but how is that? That's just making energy, isn't it, Devin?
It's transferring matter, like it's switching the hydrogen. Is it hydrogens into helium?
Mostly, almost all hydrogens, yep.
And then it's creating energy from that.
Right.
So it's not really creating it, it's just transferring it from.
Yeah, from something that's not energy, which is a little weird.
Energy, I don't know.
You're right. You're on the right track. We haven't really studied that part yet. We take two hydrogens, we add them to make a helium. The problem is this helium is lighter than those two hydrogens were. It's given up mass somewhere. Einstein's famous equation that everyone has seen, although at this point you might not understand, says that, oh, well, there's actually an equivalence between mass and energy. So if we lose a little bit of mass, we can create a little bit of energy. And so that doesn't break the law of conservation of energy because there's this relationship between mass and energy. But it is sort of a special case. That only happens basically in stars. Okay, and then the next one, the text describes how eating a snack releases enough energy to lift a 65 kilogram hiker 1,600 meters, but then says that at a more realistic conversion efficiency of 50%, the change in height would be 800 meters. So if that's more realistic, that it actually happens, aren't we losing energy there? We're losing half of the energy in that candy bar. We know we can't. Where's it going? I don't think anyone from this side has answered, although I know I read some good answers from this side. Where's that extra 800, well, not 800 calories, but however much it was? Where's that half of that energy going? If it's not going into the climber changing his potential energy or her potential energy. What's that? Heat in the air? How does it get heat into the air?
Not just into the air. It
Goes away? I don't like that answer. No me gusta. Heat I like. I liked the heat part. What do you mean heat? What's making heat?
Yeah,
Oh.
you just said into the air.
Oh, then I didn't like that answer at all.
So heat in the air.
Okay, so heat in the air I like, but how is it getting from candy bar to heat to in the air?
Friction, chewing.
Not that much.
You give off heat.
You give off a lot of heat though. We're not that efficient, so we don't turn our calories into kinetic energy. We turn a lot of it into heat energy, which is sort of kinetic energy of the atoms themselves, and then that we give off to our surroundings into the air. So that's where we lose most of our energy, is actually keeping us warm. And certainly climbing a mountain would do that, or hiking up a mountain. Okay. Let's talk about where this is going now. So yesterday, we built this, you'll want a little bit in your notes for this. Yesterday we talked about how we could describe how much work is done on an object by measuring, first day, how much its change in potential energy was. And then second day, we could also look at a change in kinetic energy. And so this we called the mechanical energy from the readings. And if we measure a change in this, we must have done some work. If we measure no change, just transfer from one to the other, no work is actually done on the object. It has the same amount of mechanical energy that it had before. It's just shifted from one thing to another. If we're talking about conservative forces, gravity is a good example. Those don't change the amount of mechanical energy an object has. So in other words, our work up here done on the object is zero, or 0 G. And so if we're only dealing with gravity, say, like something being thrown up into the air, as it's rising, as it's falling, that fits us really well. There's a whole other class, though, of non-conservative forces. And that could be, for example, friction, an outside push, not from gravity, like from you. Lots of things. Drag is a form of friction. Those do change the total mechanical energy. They could add energy to it, or they could remove energy. So a good example is you push something across the table. You have a non-conservative force with your push. It moves. It changes that object's kinetic energy. But then it stops after a little bit because friction took it back out. Another non-conservative force. Do you have a question, Devin? Oh. Let's take an example. let's say you push a 5 kilogram rock. Let's make it a curling stone. I don't know how much what their mass is, but we're going to say that maybe it's a junior league. With 50 newtons of force, and your launch is probably only about half a meter, or 0.5 meters. How fast will the stone be going at release? Okay, so this is a non-conservative force. We're adding some energy to it. How do we figure out how much work is being done on the stone?
Couldn't you make the equation for height?
Have you watched curling?
That?
Have you watched curling?
I'm saying instead of doing height, do like the length.
We can't make up a new equation for that. I get you now, what you're saying, but we can't make up a new equation for that. So, yes, Deb.
You apply 50 newtons over a half a meter, so would you just multiply 50 by...
We know how to tell how much work is being done on it, right? We have two expressions for work that we've learned. One is, the first one was that it's a force times a distance, or displacement, times the cosine of the angle between them. This will wind up similar to what you were saying, Marty. And then the other is that work is a change in potential energy plus a change in kinetic energy. This represents the non-conservative forces. Say non-con. This represents the conservative forces. But in this situation, if I'm adding energy to it, these two amounts have to be equal. The change in the mechanical energy must be equal to the amount that I put in. So I can write that as the force times the distance through which I applied it, times the cosine of the angle between them, and in a curling stone, my force is that way, my displacement is that way. So what's theta? What's the angle? 0. So this term is just 1. That must be equal to the change in potential energy, mgh2 minus mgh1, plus the change in kinetic energy, mv2 squared minus 1/2 mv1 squared. This is how a lot of our problems are going to look at the start from here on. We'll actually even add some stuff over to this side, but we're going to start with this. But don't be overly fearful of it, because what we're going to also do is draw a little picture to help us visualize it, and then we'll actually be able to simplify that quite a bit. So let's call this point 1. At point 1, I want to list a height and a speed. And then this is going to get pushed. No more force acting on it, but it will have a height and a speed again. And I want to label as many of those as I possibly can. Let's start with the easiest one. As I start pushing, how fast is my rock going? 0. By the way, if you haven't had a chance to watch curling, you should. And even better, play curling. I have not played curling, but I want to. Yeah. We recorded like 30 hours of curling. We did go pretty fast through it. Kind of watched it on fast forward, but it was still neat.
I played foreman's curling with like 2-pound barbell weights and like plastic on the floor.
That's
like
weird.
We put like saran wrap on the floor. Really, you were there, weren't you?
It was like, yeah.
Okay.
And we put like plastic.
Did you like coat the plastic with Vaseline or anything like
Well,
that?
it wasn't like, I don't know. I
It
don't know.
wasn't saran wrap,
It
it was
wasn't
living
saran wrap. It
things.
was like almost like a
Gotcha.
kind of a thing.
Yeah.
And then
okay.
on the waist we put like a plastic.
It was
Like a
smooth plastic
Teflon or
bits.
something,
Yeah.
so it would slide. Okay,
Yeah.
that's cool.
It was fun.
It wasn't any
Um,
sweeping though.
Yeah.
Now, we want to find out how fast it's going, so we don't know V2. What can we say about H1 and H2?
Both zero.
They're both the same anyway. And yes, here's a trick, we can always call one of them 0 for convenience. Because remember, this really the only thing that matters about this is how much it changes. Not where it started, not where it finished, just how much it changed. So if I can call one 0, this is a flat playing field, I can call the other 0. Let's see what that does to our equation. Well, H1 is 0, so this term goes away. H2 is 0, that term goes away. And V1 is 0. That term goes away. And so what we're left with is we've got this on the right. We said that this term is equal to 1 because the cosine of the angle between them is 0. So we can rewrite our big long exterior equation as F times D, the force I applied times the distance I applied it, is equal to 1/2 mv2 squared. And we want to find v2. And now I can rearrange this. I'll multiply both sides by 2. I'll divide it by my m. That would still leave me as v2 squared. So I'll take the square root, and that's equal to v2. And now we just plug in numbers. 2 times, I had 50 newtons, times 0.5 meters, over the mass of 5 kilograms. Point something? 3.16? Oh, 3.2 because I only put 2 sig figs there. What units am I going to have left? Joules? Let's see. We have newtons up here. We know newton is a kilogram meters per second squared times a meter over a kilogram. So I've got kilograms and kilograms. What does this make? Meters, I heard somebody mumble it. Meters squared per second squared. And then I take the square root. Meters per second. Well, that's a great unit for a velocity. So I feel confident that I did it right. What I want you to highlight in your notes is the equation we started with here. Because we're going to be using that quite a lot over the next few weeks, 2, 3 weeks, up until Christmas. We're going to add a little bit to the right. This doesn't get much more complicated, other than and I don't even know that we are, but other than if we were dealing with more than one force, we would have more than one term that looks like this, because maybe 2 things would be adding or subtracting energy. But otherwise, it's going to look like this. We're going to be able to cross out a lot of those terms as we go forward because of the way we set things up. We also don't have to worry about intermediate steps. Like, I'm looking at the very beginning. Now I'm doing something in there. I'm adding a force through a distance, and then I'm looking at the end. I don't have to worry about looking at this. Well, okay, first I have to figure out the step where I'm pushing the stone, and then I'm letting go of the stone, and maybe we have some friction in there. We can lump it all together and solve it at one time. And it does get to be pretty long, but since we can cross a lot out, we can simplify it very quickly. We're going to practice this today, and I believe tomorrow. Yes, good news. And tomorrow, with more pig problems. Yes. More pig problems. So the rest of today and all of tomorrow is work time. If you're finishing up the last homework, that's cool. Ask questions about that, and then can get on to the next one.
I have a question about this.
So, hopefully this loads quickly. question is, yeah, we're in trouble. Question is, if we have a spring, which this homework starts out with, and we want to find the work done, well, that's a variable force. The force is given as K times X. The spring constant times however much it's compressed or stretched. It doesn't matter which for springs. But how did we say we had to deal with variable forces to find the work? I will give you a hint.
Find the area.
Find the area. So if we have our force here and our spring stretch here, you'd be pulling along that. That's going to be a line. It's Kx. Well, it's going to look like this. It'll have a slope of K and it'll just keep going. So if we want to find how far to go out to some stretch X or X naught, we need to find the area underneath that. What is the area underneath in a triangle?
1/2 times it.
So we take 1/2 times the height of this, which is just going to be whatever this is, K times our X value, times the length of it, X. So if we want to find work of a spring, it's 1/2 K X squared. This is another term that we're going to add on to our equation. I apologize, I just didn't review enough to know that we were adding it right away. So our work equation can now become mgh2, and stick with me here, minus mgh1, 1/2 mv2 squared minus 1/2 mv1 squared, plus now the difference in these, plus 1/2 kx2 squared, whatever we stretch it to, minus 1/2 kx1 squared, whatever it started out. And often that's 0 if it's not compressed or stretched. But it's this 1/2 kx squared that when you're talking about work in a spring, you'll need.
That's a lot of equations.